Good morning. Thank you, Jack, for having us. Super excited to be here, sitting next to Ben, who is very much in the arena at the intersection of crypto and AI, and I think building one of the most compelling approaches to distributed compute. Um, and so, yeah, I'll just introduce myself very quickly. I'm a partner on the investment team at Multicoin. I've been there for about 3.5 years, spent a lot of time looking at distributed compute markets and deepened networks at large. And I think given where directionally we're headed in terms of compute, data, and models, and the importance of all three of those things over the course of the next decade, it's going to be a really interesting time at the intersection of these things. So, all right, cool. Well, we'll kick things off quickly. Ben, tell us the story of Jensen. Why are you building this? Why did you dedicate your life to it?
Sure. Yeah. So I'm Ben, the co-founder of Jensen. Very brief background on me. So I started life in the academic world doing machine learning research. So I did a PhD in deep learning when it was sort of exploding for computer vision, and I focused on neural architecture search at the time, which is optimizing the structure of deep neural networks at the same time as training them, essentially. So that is incredibly compute intensive. You're training and retraining these shards of models or models themselves over and over again to get to the best model for a particular problem. And that really highlighted for me back in 2015 how important compute was for machine learning and how limited it was. Like I just couldn't get access to GPUs. I had 8 of them under my desk in these 2 workstations that I'd built. Google were doing similar research to me, but they had 3,000 of them that they'd run for 3 weeks at a time in a data center. And we were essentially doing the same techniques. All that meant was my techniques couldn't be as good as theirs because I just didn't have the compute available, but I had everything else that I needed to do it. So long story short, that kind of was the underpinnings of my understanding of the compute problem within ML and how it's constrained. Took a brief detour, co-founded a data privacy startup, ran that for a couple of years, and generally focused on individual consumer privacy rights and our interactions with large businesses. Gave me an idea of how important data is to machine learning as well, and kind of instilled a belief in individual agency around our data, around compute, around all of the kind of resources we as individuals have that are actually required for machine learning. So that's kind of my personal background. Jensen, as has been mentioned, has been going for 4 years now. We focus on the compute problem specifically, and we're building a decentralized machine learning compute protocol. So we connect up all of the machine learning capable compute in the world and allow it to be used as a resource by anyone who wants to train a machine learning model. So any point in time when somebody wants to distill the value in data into model parameters or weights, that should be done via Jensen, is our idea. And the benefit that you get from that is this instantaneous ability to, at any point in time, access some of the compute of the world, of any kind of subset of that compute, and pay for the operations to be performed to do that value distillation. The current market right now, as we've kind of heard, is very constrained. There's supply chain reasons why it's constrained. There's provider reasons why it's constrained. People like AWS and Google Cloud can sit on top of all of these GPUs. We want to make that just a completely liquid market. So at any point in time, if you want to do that value distillation, you might do it on a GPU in a data center somewhere, but you might do it on everyone in here's iPhone. You might do it on everybody's MacBook. You might do it on one MacBook. We don't care. We're building a protocol that sits underneath that, a bit like TCP/IP, and just enables that always-on communication between compute nodes. The crucial difference is there's a base cost to compute that has to be paid. So TCP/IP, it's like an open source protocol. To build a protocol that can unlock this compute supply, you have to have financial payments within it. And we think those financial payments should go all the way back to the owner of that compute, and that's what Jensen does. It enables this market to be completely liquid and value to flow all the way back to the person who owns the GPU, MacBook, iPhone, whatever it is in the future.
Fantastic. So I imagine everyone in the room is somewhat familiar with the idea of distributed compute markets, the core thesis being acquiring and coordinating latent hardware that exists in the world, and then making it accessible to demand-side use cases. Given that there are many different configurations of hardware, many different profiles across clock speed, bandwidth, memory, 50 other parameters, when you think of building out that distributed network, what do you think is the most compelling? What are the units of supply that you're trying to get that you think are most compelling for use cases over the next few years?
So one of the overarching kind of principles we have is we want to commoditize compute. So the current way the compute market works is very like productized. So machine learning engineers, researchers will think that they need the latest and greatest GPU from NVIDIA in order to do that task. But realistically, they could use this kind of gradient of GPUs going back down the stack, back in history, back down the kind of like power stack of these GPUs. They could probably use any one of those GPUs for their task and it wouldn't make a huge difference. What we want to do is make it so that those engineers don't even need to think about which GPU they're using. What they need to think about is operations. They're distilling this value into this model. If they can do that on a device, they can just do a transaction and do that. They don't need to think about, is it an H100, is it an A100, is it a V100? That's a nice thing to say, but it's obviously very hard in practice. I think in reality, it involves just deeply understanding the requirements of machine learning over these devices. So memory space on a device, very, very important. If the model doesn't fit on the device, there's very little you can do, basically. But we want to build primitives that mean that you could shard that model. So if somebody comes along and says, I have this 24 gigabyte model, actually, if you have devices with low enough latency between them, you can split that into 4 models. And those 4 models can split over different devices. And depending on the cost of those devices, that could actually be way more efficient for that company. And I think companies do this manually now, but you need infrastructure teams to do that for you. We're building those primitives so that you don't need those infrastructure teams anymore. You're just running against the world's compute supply in whatever kind of configuration works for your task at the cost point that works for you. So you could pay a bit more, you could have it kind of done faster, or you could split it less and you could kind of pay more for these more powerful devices. But ultimately, it's that it should be kind of agnostic to the person. They just need access to compute, they need the model to be trained, and that's what they're paying for. They're not paying for the label of an H100 or something like that.
Yeah, and so I think that layer of abstraction is super important, right? It feels as though you're getting as close to almost interacting with that bare metal in whatever configuration it exists, and you're not prescriptive about how an engineer should use Kubernetes or Ray or Anyscale or any of these other frameworks that are out there. So on top of just having a structurally cheaper cost, advantage there, you're flexible enough to allow people to do whatever they need to, which is great. I guess given that setup, you've talked a lot about what ideology, the ideology of building distributed compute markets and what you can, enable through a distributed supply. And one thing you've mentioned before is sort of the verification problem or the replication problem. Could you lay that out for us in terms of why that's important for building these sorts of markets?
Yeah, sure. So I think the verification problem to us is the biggest problem that you have to solve in a compute marketplace like this. And very, very simply, it's can you trust the device that you're sending your model to? Do you know that they're actually going to do the work that you're sending to them? Or are they going to do some other work and try and game the system? And if you look at like the kind of dark forest of Ethereum or something, as soon as we've got this network where anyone can join at any point in time, which is required to have the maximum scale, then you've got this opportunity for people, even just financially rational actors, to maybe do 50% of the work but get paid for 100%. And if they're just operating on pure financials, if they're going to get away with that, we assume that they will do that. And we've seen that in crypto networks so many times. So we believe that the only way to build a network like this that can persist and actually solve this problem is to be able to verify those operations themselves. And there's various shortcuts you can take. You can have proxy incentives that look like they will do verification, but ultimately we don't think those will work. Those incentives become a different incentive for the person with the compute. So if you had a kind of higher level incentive, you say, well, optimize this model and I'll check the performance, and then I'll assume that the work that was specified by the original submitter has been done. Actually, you're not incentivizing people to do work, you're incentivizing people to beat that optimization benchmark. And there are different ways they could do that. We've seen this in other networks where people just end up caching responses, for example, where actually you can just very quickly beat some benchmark because you've got a response from a different request you did before. You haven't done the work specified by the user, you've beaten the benchmark, but you might have actually not achieved the thing the user wanted to achieve. So for us to actually get all the way to solving the problem, you need to do exactly what the user expects, the submitter of that task. And the only way to verify that is to verify the actual operations that the user is asked to be performed. Very, very tricky problem to solve, but ultimately I think it's the only way to actually build a network that can underpin all of machine learning compute. Back to that TCP/IP point, this needs to be a primitive protocol that only distributes the compute tasks around. There'll be plenty of other protocols that do other things. Those incentivized optimization protocols, they have a space in the world. They're interesting. They allow us to build models that maybe we'd never thought of before, but they need to sit on top of a verified compute layer. Otherwise, they'll be abused, and we'll have extraction from the system where the outflows are greater than the inflows, and eventually the protocol collapses. It can't be persistent forever without that verification at the bottom.
Yeah, I think we've all seen sort of less deterministic approaches to that verification problem through, rankings or badges or status get gamed very easily, and so having it done at that unit kind of mechanical level definitely seems like an unlock. So I guess given that, right, like there's almost two models of the world. There is, I guess you could classify this as the skeuomorphic world where there are existing machine learning workloads that are going to AWS or CoreWeave or Lambda Labs, and you can build up a parallel cloud through this distributed, compute network, and then submit workloads to them, and you're basically just sort of ripping out one piece of metal for another. But there's theoretically novel application layer things that you can do when you have those verification guarantees, right? Like net new things to build on that are not just potentially cheaper compute. And so I'm curious to get a sense of like how you think about that design space, what's compelling there, what can you uniquely enable with this network that you cannot do on bare metal servers in a centralized capacity.
Yeah, I think I've explained this a few times this week and in different ways, but the way we think about it is there's two sides to this problem. There's a backward-looking side, which is the machine learning compute problem itself that we talked about, the chip shortages, the rent seekers in the middle of the market, the fact that it's crazy expensive because you're paying someone's profit rather than actually paying for the devices themselves. You can solve that problem in a decentralized way by standing up an AWS-like interface and allowing people to book time on GPUs. It's just you're using latent supply, and as long as you've got some version of verification, you can grow that to a certain size. We don't think it can kind of persist, but you can actually improve that marketplace right now. And we've seen greater competition in the GPU marketplaces anyway. There's new, like people like Lambda have come in a while ago now, but they're offering competition to AWS and Google Cloud. So like it is kind of getting a bit more competitive and prices are coming down. You can do the same with decentralization. But to us, that's a 10 to 20% improvement on the current situation. It's not that step change that you mentioned. The step change is the second half, which is the forward-looking half. And then that's what can ML become in the future? And we at Jensen, we think about this as the machine intelligence revolution. The last kind of technical revolution was the internet. It was the connectivity. This revolution to us is changing the way we think about technology away from interacting with imperative code to interacting with models. It'll be probabilistic interactions that we're all having. So when you're using an app, right now you're just going through the flow of some code that somebody's written. It's a predetermined kind of path. In the future, you'll be interacting with a model, and we have the rudimentary version of this now where we talk to chatbots. That'll be abstracted away. It'll be behind the UIs that we're interacting with. It'll be behind all of the technology we're using. And to us, this is a new version of the internet. The internet right now is a set of text. It's a huge network of rich text that we can navigate and we can query through language. In the future, that'll be a huge embedding space. It'll be pieces of models where value and data has been distilled into those models, and queries are inference. It's asking that model to predict something for us. And this is a completely new way of thinking about technology, but it's much, much richer, and it's much better for us as humans to interact in that way. But for that to exist, certain base resources need to be much more accessible than they are now. So compute's the kind of obviously the one we think about the most. There's data exists as well. We need data protocols to solve this. But on the compute side, if you think about those models, they're always going to be running. They're always going to be updating. There'll be pieces of model updating on all of our devices, all of the servers we interact with, constantly being used. Those models need access to compute. And right now, they have to kind of go out into the human world. Somebody has to book time on a GPU for them, and then they can run on that GPU, and then they can return the answer. That's way too slow. It just cannot scale. What needs to happen is that model needs to be able to interact with the resource directly. It needs to be able to say, hey, I need 100 ops of compute, and I have a wallet address here with payments ready. Can I just have it? Can I just train myself instantly now? Can I train another model? If I need access to a new modality, if you've asked something to this model and it needs to understand vision, for example, it can train a vision model quickly, or it can access another vision model. So the future of machine learning very, very quickly, in our opinion, is going to move from people training models to models training models. And the infrastructure for models to train models needs to be programmatic. And right now, it's way too human-based. Web3 and crypto gives us programmatic payments, which enables loads of this stuff. But once you've got the payments, you need the core resource itself. And we're connecting that core resource of compute to this payments infrastructure that we've already built to allow those models to just interact with that resource whenever they need to. But yeah, like I said, the other bits need to be built. Somebody needs to build the data portion. Somebody needs to build the human labeling portion. We're very excited about those things. And like, if anybody does want to build those, please talk to us. We don't want to own them in any way. They need to exist for our vision to exist. So we're happy to share any knowledge we have, any thoughts we have to people who want to build those things. Because basically we're very early, but we have a very clear vision of what's going to happen. And a few things are needed for that to happen.
That's pretty sick. You've been pretty laser focused on training. I think conventional wisdom is that training is much more sort of high, like bandwidth dependent, latency dependent. You need much more performant GPUs. How do you sort of address that with a distributed network? And what is sort of the architecture design decisions that you've made specifically for training? And how does that did you see yourself extending out to inference at some point in the future? Or talk a little bit about the decision to focus on training specifically.
Sure, yeah. So training and inference, they're seemingly very similar, but actually very different. In our opinion, training is compute constrained. So typically the biggest bottleneck of training is getting access to powerful enough compute to do that value distillation. Inference is latency constrained. We can optimize inference very heavily, and anyone who's doing inference in the Web 2 world now will heavily quantize their inference models. They'll put them on CPU. They'll make them really, really fast, because once we've got that value distilled into the model, querying it can be done in quite a few different ways, and those ways can be optimized really heavily for specific use cases. So what that means is inference itself doesn't need a huge amount of compute in a lot of cases, but it does need to return quickly. And if you think about that future that I was talking about, if when we're using an app, we get a spinning wheel and we have to wait, we're going to use a different app. So as users, we're going to index towards the app that gives us the fastest response time, which means that for inference, we have to get the lowest latency possible. So if you were to build a decentralized inference network, your challenge is getting the models as close to the user as you possibly can. That starts to look a bit like a CDN. You can build that as a decentralized network. That's perfectly viable to do, but it's harder to bootstrap because essentially the value of that network is linked to its size. It's called Metcalfe's law. Helium has it as well. Basically, the network needs to be essentially maximum size before it has maximum value for users. So you need the supply side to be massive before you can actually serve the demand side. That's a problem people can solve. It's something you could go ahead and do. For Jensen, it would be a completely different approach, which is why we don't focus on it. We focus on those compute constraints within training because what's required there is to connect up as much powerful compute as you possibly can and then provide it to the user in as commoditized way as possible. As you mentioned, though, there are latency bandwidth issues to the current way we train models. So right now, we've gone down this path of training these hyper-centralized models. They're massive. They run over 4,000 GPUs, but they need to have very fast interconnects because we shard the model in a really specific way. I think what the machine learning world has kind of forgotten is we've only been doing that for a few years, and it's just one of the ways of doing it. It's not the only way, and I think people start to think that it is the only way. The way we view it is these massive models like GPT-4, the Llama models, they're all the tip of the spear of research. They show us that it's possible to do these things with models, but they're not the only way of doing them. They're just kind of the first and possibly the easiest way or the first way that we found to do them. What comes after that, and if you look back at kind of development of technology in general, is a long process of actually productizing all of that stuff and making it work for most use cases. And what the space needs, I think, mostly is distributed systems engineering knowledge, because actually we're doing those models in a very, very fragile way. We're treating them as this kind of thing that we have to carefully train, and if a portion of it doesn't work, we kill that $10 million training run and we start another one. That's not how we do distributed systems. In distributed systems, we have replication, we have redundancy, we have nodes that can fall in and out, and that's how we're building Jensen. It's to build it in this old way but new for machine learning, where we acknowledge a load of old distributed systems principles, and if we've brought down the cost of compute, we can do more replication, we can have more redundancy, we can have more failover. And I think when you do that, actually you remove those scaling limits on models. The large tech companies now, they're unable to keep building bigger models forever because they're hitting data center size limits. They're not hitting money limits. They can buy as many GPUs as they want, but they can't put them in one place because it's hard to find a data center that can actually support that for geographical reasons. What Jensen thinks is instead of us trying to like inch that up and make a model with another 100 GPUs in it, let's just unlock all of the GPUs in the world, build a model in a slightly different way, and remove the scaling limits entirely. There'll be downsides to that with latency and things, but we can walk around those. We've had distributed systems knowledge for a while now. So a lot of the research we do is along those lines. It's how do we build a model that instead of being on 4,000 GPUs in a data center is on 1 million or 1 billion GPUs.
Got it. I think I would argue that the single most important insight in what you're building is sort of the importance of verification and sort of more broadly proofs of computational integrity. And you sort of talked a little bit about how that applies at the compute layer. How do you think that implies at maybe other layers of the stack, potentially models and data? It feels like, when the pace of production at the application layer is moving so quickly, there might be potentially important primitives around identity and stamping and such. How do you see compute verification impacting other layers of the stack, and that's sort of kind of flowing back into compute in some way?
Yeah, I think we need that verification, and we need attribution at all layers of the stack to get the full kind of vision of the future that I described earlier. I think probably one of the issues is it needs to flow all the way through. So it needs to start at data provenance and identity, like you mentioned. It needs to go through the data labeling and through the data augmentations. It needs to go through training, and then it needs to go through inference. And so different people are building the different pieces of these stacks. We're building the compute part, and nobody else is building that. So at the moment, whenever we hear messages about people saying, well, hey, we can do attribution from inference back to the data, if you can't do that attribution through the training process, you can't do that. You can't get back to the data that was trained into that model because you've got a missing link in the chain. So we build a missing link in the chain for everybody else, but everybody else builds the links in the chain for us as well. And ultimately, I think what will need to happen is just an agreement between the various protocols in the space as to how we pass that data around. So when a model comes out of Jensen, we want to make sure that when inference is performed, it can go back through into Jensen, and we can say, oh, this inference generated however much value it generated, that value should go back through to the person who trained the model, but also to the person who designed the model, and also to the person who gave the data that went into the model. And once we've got that, we get a much better ecosystem of machine learning, because right now there's way too many portions where a company can just extract value by saying, well, I own the data. Facebook, for example, we all give our data to Facebook in order to use it, and then Facebook uses that data to train models, but where's the attribution back through to us? It doesn't exist because it has to go into this black box centralized company. One of the most powerful things about decentralized technologies is that open transparency. We know the value that was given to this model. We know where it came from. So Jensen is an essential link in that chain, but for our vision, there's other essential links. And one of the kind of call outs that we say to people is, look, if you're building one of the other links, let's talk. Let's figure out a way that we can trade that information between the two networks. We think in the future, it'll be very, very multi-node. So in the situation I described where Jensen's running on every single compute device in the world, it'll be running next to data protocol as well. The users give their data to these protocols and they can have attribution back. Users will also do labeling. There'll be all of these nodes sitting next to each other, and those nodes need to be able to talk to each other. So when a user comes to Jensen and says, hey, I want to train this model on this data here, instead of having this big chunk of data in S3 or an IPFS, they can say, use the data that's local to these devices and pass the attribution back to the data network, and then that can go back to the user. I do have a kind of personal beef with the idea of us just being directly paid for our data. I think in my previous life, when I was looking at privacy, there's never really been a good enough reason to pay users a particularly large amount for their data. I think realistically what we'll have is gamified data collection, where in the games that we interact with, in the media that we interact with, in the apps that we use, it's actually a kind of richer experience for us rather than you get a check for like $1,000 a month because you've put data into a model. I think that's unlikely, more likely than it used to be. There used to be only advertising that could pay you that. Now there's model training, but still, I think there needs to be new mechanisms there. And I think the data protocols need to think about this. They actually need to focus on the user and how they're engaging the user, not on just the core of the protocol, because it's not quite enough.
Totally. I mean, what you're describing feels almost like a philosophical shift, right? Like there is sort of the way people think of deploying machine learning workloads today, and what you're describing is sort of fundamentally, different in a lot of different ways. And so I'm curious, when you think about a developer ecosystem potentially on top of Jensen, one in which the people building these systems or other forms of abstraction layers or whatever, or applications themselves are bought into sort of this vision. What does that look like? What are the bottlenecks to that? How do you take an ML engineer who's been at Stripe for 10 years or whatever to like shift the way they view the world? Do you see that as within the mandate of Jensen itself, broadly the space? How do we get more people bought into the idea of verification at the core of all of these systems?
I think just by giving them good tech that works better than what they currently have. I think it's an iterative process. I've talked a lot about this kind of long term, how the world will change. And in reality, obviously that is what we see, but you don't just instantly get there. Like it is stepwise to get there. And I think the way we do that is finding out what the most kind of like core primitive is that matters for those users right now and solving that problem. So back to the kind of backwards looking point, Jensen represents just cheaper, higher scale compute that more people have access to. So right now, if you're a machine learning engineer and you want to train a model on a single device, maybe you've got a GPU, you can do that. But you've got this fantastic idea for a new machine learning enabled app and you want to scale that up. You're just one person and you think, well, I need 50 GPUs to do that. You're really going to struggle to get those GPUs. And you're going to have to learn a lot of stuff about the GPU marketplace, about the infrastructure. You're going to have you're going to have to SSH into these machines. You'll have to set up virtual machines. You have to do all this stuff that is outside of what your core kind of value proposal is, which is this new rich kind of experience that you've designed in your head. And I think we saw this back in the cloud world as we shifted to serverless, where originally developers would have to set up entirely new application servers and they'd have to become infrastructure engineers and sysadmins and they'd have to do all this extra work to actually get their app up and running. And then Heroku came along and said, hey, we've commoditized all that, we've packaged that up, you can go back to what you're good at, which is designing and building this app, and then you just do one click and you deploy it. Jensen wants to do that for machine learning engineers, where you stop thinking about GPUs. You shouldn't be thinking as a developer, do I need an A100 or an H100? You should just be thinking, hey, I've got this great idea and it needs to train somewhere. I can do one click and I can make it go and train on some devices somewhere in the world. That bit is completely abstracted to me and commoditized away. So I think that's the biggest reason we'll get these developers in, because we'll change their view of compute away from this really difficult problem to something that's similar to serverless. It's just like, okay, that resource is always there. I know I have to pay for it, but I can see a order book price or kind of like some price discovery mechanism price immediately available to me. I know how much it'll cost and I just need to trigger the training. I don't need to think about anything else.
Yeah, I think you mentioned a little bit earlier, eroding margins as a core value proposition here, and thinking about pricing compute at cost and coming to sort of like a fair market value. Obviously, if you look at hourly instance reservations between AWS and Lambda and CoreWeave, you'll see like slight fluctuations, and there are potential arbitrages in that market and not easily expressible, right? But those gaps shouldn't theoretically be there. And I imagine the end state of Jensen is a world in which you can, at any given time, have the market rate for a unit of compute and then just book it immediately. That's fascinating. How does price discovery happen in that world, right? Is there like a limit order book? Is there an auction happening? Like, how do you build fair markets around this, like treating compute as a commodity? Because it feels so inefficient today in and of itself.
Yeah, that's a really good question. It's something we're still working on. We're doing research on that because there are different ways that you can do it. You could just do an order book. That's probably the simplest way. It requires the compute to be very, very commoditized. Otherwise, you're going to have multiple order books. But it's probably the simplest and kind of easiest to think about method. On top of that, you can have AMMs sitting on top of that. They have to work a bit differently because the dynamics are different over compute, but you can kind of envision a world where that exists and makes it more efficient. And then you can have auction mechanisms where you're having direct price discovery between participants. You can have first order auctions, you can have second order, you can have lots of different kind of ways of doing it. And I think ultimately The solution will probably be a combination, but like I said, we're researching that right now to figure out what the best one is. It is a bit different for compute than it would be for just a normal financial asset. So there's things you need to kind of think about before just going straight to an order book. But I think whatever happens, we'll have a much more efficient mechanism than we have right now, because ultimately you're just connecting up the direct supply participant themselves and the demand side user, rather than going through this kind of chain of middlemen who each are extracting some kind of rent from the process.
Sweet. Ben, I think we could jam here for another hour, but I think we're up on time. So where can people learn more about Jensen?
Check out our website, Gensen.ai. Check us out on Twitter, Jensen AI, and drop us a message on any kind of one of those mediums. And if you want to chat, if you're doing anything that's close to us, we'd love to talk about the kind of standardization and integration that we mentioned. I'm on Twitter as well, at FenBuilding. Drop me a message, happy to chat. And you can sign up for waitlists to be a supply side participant or a demand side participant on our website. So please do that. We'll reach out to people as soon as we have something that we want you to test.
I have one quick question real quick, actually, Ben. I'm wondering if you could dive a little bit more into problems with parallelization of models on heterogeneous hardware with latency and Jensen's unique approach to handling that.
Yeah, I mean, to us, that's the second hardest problem. So the biggest one is the verification problem. Basically, you don't have a big distributed network if you can't do verification, because the thing will get exploited. So you've got to solve that first. After that, you've got this heterogeneous latency and bandwidth problem. There's two ways of solving that. One is to look at the current way that we build models and then optimize that. So you treat the distribution of a model over the devices just as an optimization problem, where the parameters are the latency and the bandwidth and the compute power. Right now, we just assume that all of those things are fixed, so we can just distribute in the same way over all of the devices. But you can actually distribute in a different way. If you have a very powerful compute device that has high latency connections, you can just do more compute on that device before communicating to the other devices. It's a careful balancing act, but if you do that, you can actually get state-of-the-art results from training a model like that over this heterogeneous system. So that's really interesting. It lets us basically take a model and the way it's trained right now and just apply an optimization wrapper around it and make it better on this infrastructure. But that's just the first way. The second way is kind of back to what I was saying before around how we've gone down this path of centralized model development. It's changing that idea. It's saying, well, let's just build an entirely new architecture of model. Instead of the constraints before where we can only have 4,000 GPUs, now we can have 1,000,000. What can we do differently with this model? And our belief is the future is not one big model. It's loads of tiny pieces of model all interacting. So when you come to query that model, when you come to run inference, when you come to run a sample through and do training, it might take a different path through different shards at every point in time. And this is a different way of viewing embedding spaces and model parameters. It's much more freeing, but it requires compute costs to come down, because the biggest reason why we do them in the centralized way now is because compute's so costly. We don't have the ability to do extra compute. We need to trim it down as much as possible. But once we open this up, we can do extra compute. We can chart these different paths through these different models, and then you get different modalities and things being combined as and when you need to. We do this process now really manually. If you wanted to take a language model and allow it to talk about images, you would, as an engineer, basically rip those two models apart and kind of stick them together in this manual process. It's a bit more finesse than that, but realistically, that's what people are doing. We can automate that process. We can make that happen at any point in time. It can happen on every query, on every training update, and it could happen with different vision models, different audio models, different modalities at any point in time. So I think it's taking what we do manually now and making it automated by building technical primitives that allow that to happen instantaneously, rather than by a person sat in front of a terminal or a Jupyter notebook, kind of doing it manually on the data structures.
Awesome. Thanks so much, guys. Can we get a round of applause, please, for Ben and Cheyenne? That was a great talk. Thank you guys so much. Awesome.